Okay, welcome to the second week of Intelligent Robotics class here in University of Texas in Alamo City called San Antonio. Now, for those students who are in North Carolina, I just want to let you know that your homework is almost similar to what we have here in Texas, except that Dr. Karimundini, your instructor, has made some a small modification, but nevertheless, if you look at this particular, report, it was done by very capable people. You can see that there is a mathematical model of the inverted pendulum system of equations here. The reason I'm actually giving you this first homework and the first experiment, I'm familiarizing you with manipulated robotics. Inverted pendulum is a single-link robot, you see. And double pendulum is a two-link robot, okay? Except that a lot of times in textbooks, you see two-link robot to be on a plane. It's a planar robot for ease of calculation, ease of analysis. However, the inverted pendulum is in 3D in the lab. So you'll be doing 3D control of a two-link robot. I want you to study this carefully. Don't worry about the end of it, the root law, because these are not part of the homework, but only basically mathematical work. This area I want you to do. And then you need to create a state equation, nonlinear state equation for your dynamic model of the pendulum. Then you can linearize it around angular pi. Because as you know, the pendulum going up, that's pi. Coming down in a stable is 0 degree. So you are linearizing around an unstable point, what we call singular point. And then any variation around it to stabilize the robot is going to be still good for the linearized model. But if you give it too much velocity, it may fall down and become unstable again. This is something that you could exercise in the simulation. There's a lot to learn from this simple inverted pendulum, okay? And the second one on double pendulum is coming from University of Adelaide. Here you have again a mathematical model of this on page 26 is what I want you to read. Mathematical model of double inverted pendulum. This turns out to be an initial background material for you to learn. So later on when we talk about manipulated dynamics, meaning mathematical model for manipulators, is based on Euler-Lagrange concept in this section. Okay, and then we go from there. All right, now in the rest of today's lecture, I'm going to first of all mention to you that the book by Professor Cork from Australia is a comprehensive book which has all the concepts of robotics, control, and vision. And we will touch all those topics. As I mentioned, we will have a fairly good coverage on the vision part and the machine vision, because we have 15 cameras in the lab that you will be using as part of your project. Some of you are doing visual SLAM and so forth. What I'm going to be talking today about, I'm going to give you an initial detailed lecture on kinematics, forward and inverse kinematics, and that lecture of today is going to be based on basically the following portion of your book. Chapter 1 about the book, so you can read it and find out basically what it has done. One of the issues that I've been using this book, now this is the third year I'm using it. And one of the issues with the book, which I feel a little bit uncomfortable, is that if the complicated concepts of robot, manipulated robot and mobile robot and so forth are covered in the book, but in order for you to reinforce your learning, they go to the MATLAB toolbar. Okay? And you're not here to learn MATLAB, you're here to learn robotics. So that's why I'm giving you lectures outside of the text. And I would like you to review the lecture of today on kinematics in both versions, first of all. And then you will want you to go to read chapter 1, chapter 2, chapter 3, and then all the way to chapter 6. No, chapter 7, robot arm kinematics. So the crux of my lecture today is embedded in chapter 7 of the book. Okay? And don't read it until you review all the stuff in the lecture that I'm covering today. Okay, but you will be later on, you will have guest lectures on robot toolbox, on MATLAB and Simulink, and you will be using it probably in homework number 2. Very comprehensive, you work all aspects of what you learn in the lecture, you do it on MATLAB toolbox. Okay. Now let's go to this set of slides, and we are going to basically study robot kinematics. What is kinematics? Robot kinematics is a study of the geometry of motion of a manipulated robot or robot arm with respect to a fixed reference coordinate system, without regard to the force, moment, and moments which cause the motion. Okay? So, if we want to basically worry about the cause of the motion, we'll worry about that when we want to control the system later. We just want to know how the arm moves, okay, regardless of what made it to move. And as we said before, in last week's lecture, 2 elements are important in kinematics: rotation and translation. Okay. You want to go from point A to point B. Imagine that my hand is a 6-link robot. Industrial robots are all 6-link minimum. I want to go from A to B, so I move all of my joints. I have one here, the base. I have a shoulder, I have an elbow, that's 3 degrees of freedom, and I have 3 at the wrist, at the end effector. That's the end effector. Pitch, yaw, and roll, okay? So I can move all those things and get to this point. This is forward kinematics. But the most important problem in kinematics, which is much more difficult, is the inverse kinematic. Because why is it important? Is because once I reach this point, up to here, I'm working in 6 different coordinate systems. Each joint has its own coordinate system. Joint 1, joint 2, joint 3, all the way to joint 6. Okay. This all is called joint space. When I come to the real world, when I'm trying to, let's say, work on a product in real space, then I have another coordinate system just off of my tip of my end effector. That's called Cartesian space. Cartesian space is the real space. And you have, later on you see you have a transformation going from end effector to Cartesian space. We call that Jacobian matrix. Jacobian matrix is the transformation of moving from joint space to Cartesian space. That's very important because you need the robot to work in real world. That's all you don't want just to dance for you. Okay? You just want it to do real work, and you need to be able to not only get to the real world and get, let's say, in minimum velocity or zero velocity or zero force, so that you don't damage what you're trying to do. Okay? So, inverse kinematic has infinite solutions, unfortunately. As you will see today or maybe even next time, I'm going to be confronting with the upper part of the homogeneous transformation matrix. Remember homogeneous transformation matrix, which was, I can show it to you here one more time. Homogeneous transformation matrix has a Cartesian rotation part, 3 by 3 rotation matrix. It also has a 3 by 1 translational vector. Okay. If you look at the top part of this matrix, you're talking about 3 by 4, 12 elements. It turns out that if you study the inverse kinematic problem carefully, you have to solve for 6 unknowns, the joint angle from base all the way to the tip of your end effector, 6 unknowns. If it's a revolute robot, which all of them are rotational, you have 6 angular position, theta 1 to theta 6. But how many unknowns you have in equation? You have 3 by 4, 12 equations, or nonlinear algebraic equations. That's why inverse kinematic has infinite solution. You have 6 unknowns and 12 equations. You only want one of the solution, the one which works. Okay. So we'll get to that, and you'll see it much better later on. So you've seen that before. We saw that last week. These are the consortium of tools and areas and disciplines that put together in order to serve justice for a robotic education and robotic study. Kinematics we are talking about right now. Later on we talk about dynamics, which is related to that second file I gave you for the homework one, dynamics. The Euler-Lagrange or Newton-Lagrange equations. These are mathematical model basics, principles, to be able to find a mathematical model for a set of a chain of links together, like a chain. Task planning is to plan from A to B, how you want to move robot from there to there. A lot of times you do it in steps, because if you go too fast, you may be, breaking something or damaging something. Then, of course, software is everywhere that you're going to be doing. Sensors, vision and tactile sensors, touch sensors, velocity and position sensors, and so forth. The inverted pendulum in the lab is going to have a position sensor in the pivot of the rope of the pendulum. Then you can measure it, and then through the software that you're going to be dealing with, coming from the manufacturer, you can estimate the velocity of the pendulum, theta dot, the angular velocity. And of course, control system will come in toward the middle to the end of semester, and you have a lot of mechanical design and actuators, motors, every joint. Every joint will have a motor. Okay. So, again, we are dealing with kinematic problem. You want to look at controlling a robot end effector in a Cartesian space, and each joint of the robot has its own, as I said, coordinate reference system. Okay, you are dealing maybe up to 6 coordinate system. Okay, And kinematic will allow you to go from one joint to another joint, and you can both rotate and translate from one point to another point. So kinematics is an analytical study of the geometry of motion of the robot, again without the regard to the causes of it. You saw this before. Here you have a vision system, a camera, two-link manipulator with a fixed end effector. You have a ball, you want to pick it up. You have a base frame. Your base will have its own first coordinate system. You have the second link is another coordinate system, and the one at the tool frame. So there is a coordinate with the tool frame, the very end of your end effector. You also have a coordinate frame for the target material you want to pick up, the ball, and you of course have a camera. So you have all these coordinates are all working simultaneously together, and you will learn that the robot has to take into account from base how much to move from. I have a laser pointer. Let me find it. How much you rotate around the base, how much you rotate around link frame, how much you rotate here, in harmony with the camera and frame, and so that this end effector knows exactly where to come in its inverse kinematic problem. There's only one solution for this robot, inverse kinematic problem in here, right now. It cannot go here, it cannot go there, it cannot be going somewhere which is not reachable. That's many problems, solutions which we don't want. So, between two frames, we have a kinematic relationship. Basically, a translation and rotation, as you saw before. So, if you want to go here, you can move here and then rotate, you get this. So, Z is here, it's now going downward. Y is going that direction, is now this direction, and X is going this way, going that direction. And so, as you already have seen, this relationship mathematically represented by a 4x4 homogeneous transformation matrix. The top are the key information. Here it is. This is the amount of translation that the robot moved. You could have a robot move here and then goes here. That's the translation. Or you could have a link which goes like this, and then you rotate it, you go there. If you have only translation between joint I and joint I plus 1, it's called charismatic link. Charismatic link. In about 50 years ago, University of Stanford built one of the first charismatic robot. Okay, call it Stanford R. You can Google it and find out the history behind it. Now, if every joint of the robot is rotational, like what I'm demonstrating here, they're all rotating around a z-axis coming out of the joint. Okay, here, or down here, joint like this. This is called revolute joint. Okay, revolute joint. So this part, therefore, is the 3x3 rotational matrix, and is 3x1 vector. And this is called perspective, which we don't really apply that much. And then we have a scale, a global scale one. So for our practical purpose, you could really ignore the last row. Okay. In some cases, you may have other than one where you actually are enlarging or contracting the relationship between one joint to another joint. So, kinematic consideration, we will use this kinematic to describe a spatial configuration of a robot given by two approaches. Forward kinematics, given so much change in all these degrees of freedom, okay, where am I going to end up? going from here. That problem has a unique solution, no multiplicity, no problem. All you do, multiply 6 matrices together like those that you just saw, and you know where you end up. That's all it is. If you want to know where you end up after joint 1, you do 2 multiplication. Joint 3 multiplication, and so forth and so on. Okay? That's how it works. But if you want to go up to the tip of the end effector, you do 6 of those, which is the number of degrees of freedom of most industrial robots. Speaking of industrial robot, UTSA students will have a chance to work on an ABB, a state-of-the-art manipulator. This is a manipulator robot which are quite expensive, about $60,000 to $70,000. At least that's educational price. And they're about to move to Southwest Station Institute. But before it moved, the class here will do experiment on it. If it had moved, I would have taken you to the Southwest campus and do the project, do the experiment. We're going to catch it before it goes. Okay. Because I want you to have a feel about manipulated robot, and Ikram is going to be revising his experiment for that particular robot. You saw him that it wrote ACE logo on the board in our YouTube channel. So that's the forward kinematics problem. That's the easy problem. That's the unique problem. Inverse kinematics, given a desired end effector position in the Cartesian space, what are the joint angles to achieve that? Assuming that it's a revolute robot, okay? Most of them are in that situation. So that's easy. Here's the cartoon, and that's very tough. So for a robot system, the inverse kinematic problem is one of the most difficult ones to solve. The robot controller must solve a set of nonlinear simultaneous equations. The top 3 rows of the homogeneous matrix. And you will see one equation for every one of those elements later on. Okay. The problem can be summarized as the existence of multiple solutions, the possibility of non-existing solution, and the singularity. Okay. For example, the robot could have a desired solution, which is what you like, very good. You may have goes to a place where it's so far away from the real world, so it's not even reaching it. Or the Cartesian point is outside of the workspace. Workspace of the manipulator is how far you can go and work. Okay, down, up in 3D. That's your workspace. Or you could have singularity. For example, you want to do something like that. You know, just imagine that you can do that. You know, you can work like this, or you can eat like this instead of like that. Those are not good solutions. Okay. Those are singular solutions. Okay. You may be very flexible as a kid, and you may be able to do it, but but that's not typical. So again, as you saw last time, here are 2 different ways you can approach it. So the inverse kinematic problem may have more than one solution. As long as they're feasible, it's okay. Okay, that's the case here. For a two-link robot, which is like a double pendulum, for example, that we talked about. This is a planar robot. Most of the textbooks have two-link planar robots. And this problem gets worse with more degrees of freedom. Up to two-link robot, this course is manageable if you had a real exam situation. I could not even convince myself, even if I were to be a very mean instructor, to ask you more than two-link example in the class, because it's impossible to do it in a real time. Okay, so one link or two link is handleable. You can handle it. Okay, and of course redundancy of movement. A lot of times you could have the situation where you have to have redundant robot. Make a note of that. There is another class of work called redundant robots. Where would they show up? You are in an industrial setting and you need 7, 8, 9 degrees of freedom. The Canada arm on the space station is a redundant robot. Because a lot of times you need to do something that human hand cannot do. And the astronaut is a master, is a remote controller of that robot, and actually does things that they cannot do themselves. Never mind the danger of it, but they cannot even do it. Or imagine that you have a robot in a nuclear power plant, where you need to go into the location where the nuclear rods are, and you need to clean it after, let's say, maintenance of the plant. And you may have just a small opening to go inside and do a lot of cleaning inside. 6 degrees of freedom will not work. You need to have a redundant robot which will basically go in there and cleans even close to the mouth of the container. Okay? So that's the situation. So this is the situation where the goal is outside of the workspace of the robot. Workspace of the robot is, as far as it goes, is here. Let's say a circle like that. This goal is outside. So this is the singularity, singular solution. Okay. So it is very often a singularity is a place of infinite acceleration, trajectory tracking, and that's not very good. You will see that, for example, in trajectory planning, you go from point A to a waypoint to another waypoint to the end point. Each time you stop, you have matching situation. You have coming in with the velocity and the position and going out with the same velocity to the next point. You have to have a continuity. And that condition gives you equation to find the parameters of the unknown polynomial which represent your trajectory. Okay. But in this case, the velocity is in such a way that the derivative acceleration blows up. And then you cannot do it. So joint space trajectories, we have to move from a point to a point in this space. A trajectory is a time history of position, velocity, and acceleration for each joint, as I mentioned to you. And trajectories are computed at runtime and updated at a certain rate. The path update rate, for example, like for a Puma robot, update is at 36 Hertz. Puma is the name of the first industrial robot built in the whole world, and it happened in the United States in 1961, 62. Okay. I mentioned to you that the man behind it was my late mentor, Dr. Joseph Engelberger, who was a graduate student at Columbia in 1950s in physics department, and he had a classmate, George Dewalt, and George had applied and got a robot, a patent for a robot, a machine that they didn't even know what to call it yet. And Joe, I've known Joe for about almost 15 years, 16 years. He's been to my conferences, and I've been to his house in Connecticut, and so forth. Bless his soul now. Joe realized what this guy's got. So he bought the patent of his classmate. And with that, he started a company called Unimation. Puma is the first project of that. So let me stop here, and we'll take a short 2-minute break in the class, and then we go to the next. Yeah, it was